students, welcome to this session. In this session, we are going to study the binomial theorem. In our lower classes, we have studied what binomials are. Binomials are the algebraic expressions having two terms. For example, x plus a, x minus a. And we have also studied to find the squares and cubes of these binomials using the method of repeated multiplication. For example, x plus a the whole square you would find out by multiplying x plus a with itself. So, x plus a into x plus a gave you x plus a the whole square, and this was equal to x square plus 2 into x into a plus a square. Similarly, you found out x plus a the whole cube by multiplying x plus a the whole square with x plus a, or basically you're multiplying x plus a 3 times. Okay? So, this gave us x cube plus 3x square a plus 3x a square plus a cube. So, squaring and cubing the binomials, we have got these identities. The identities a plus b the whole square, a plus b the whole cube, x minus a the whole square and x minus b the whole cube. Okay? So, we have found out such identities using the method of repeated multiplication. Now, what happens if I increase the number, increase the index over here? So, if I increase it, say x plus a to the power 4, I know I have to multiply this x plus a 4 times. So, I can write x plus a the whole square into x plus a the whole square, and I can write the formula. But if I go on increasing the value of this power, then a repeated multiplication becomes a very, very lengthy process, and it is a tedious job to find out the expansion using the repeated multiplication. And to overcome this problem, we have introduced the binomial theorem. This was first introduced by Sir Isaac Newton, and in our syllabus we are considering the powers to be positive integers only. Binomial theorem gives us the expansion of a binomial when it is raised to the nth power, and in our syllabus, as I said, we are taking the power to be positive integers only. So, let us see what this binomial theorem is. I have made a note of the expansions till the index is 4. So, we know x plus a to the power 0, anything to the power 0 is equal to 1. But we have to take the condition when x plus a is not equal to 0, because we know if we have x plus a equal to 0, then this one becomes 0 to the power 0, which is undefined. Therefore, we see to that the base is not equal to 0. X plus a to the power 1 is x plus a itself, x plus a to the power 2 is x plus a into x plus a, that gives rise to this identity x square plus 2ax plus a square. We have x plus a the whole cube is equal to x cube plus 3x square a plus 3x a square plus a cube, and x plus a to the power 4 like this. Now, using these expansion, let us make a few observations. Observe the number of terms. Index here is 0, but the number of terms is 1. Index here is 1, number of terms is 2. Similarly, index is 2, but the number of terms is 3. Same here, x plus a to the power 3 is there, but the number of terms here is 4. So, in general, if n is the index, then the number of terms will be 1 more than the index. Therefore, number of terms will be equal to n plus 1. So, this is our first observation. If the index is n, then the number of terms is 1 more than that, that is n plus 1. Now let us observe the powers of x. So power of x here is 1, power of x over here there is nothing, means it has to be x to the power 0, because we know x to the power 0 is equal to 1 and a into 1 will give us back a. So observe the powers of x over here. We start with 2, same as that of the index of x plus a. So we start with 2, then we have x to the power 1, here we have x to the power 0. For the next expansion, you see we start with 3, here we have 2, here we have 1, and this last term has x to the power 0. The last expansion that I have written down, we start with 4, sorry, this has to be 3, okay. We start with 4, x to the power 3, x square, x to the power 1 and x to the power 0. So what is happening here? We raise the power of x to the highest, that is same as that of the index, and we reduce it each time with 1 until we reach 0. So the power of x, second observation, power of x reduces by 1 to reach 0. So we start with n and we reach the term 0. Okay. Now let us observe the powers of a. Here there is nothing, so we can write a to the power 0. Here we have a power 1. There is nothing here, so we can write a to the power 0. We have a power 1, a to the power 2. Here a to the power 0, a power 1, a power 2, a power 3. For the last one, a to the power 0, a to the power 1, a to the power 2, a to the power 3 and a to the power 4. So what is happening here? The power of a is increasing. We have the power of a increases by 1 for each successive terms. Okay. So we start with the 0 and we reach n. For the last term, we will have to the power n. Fourth observation, observe the sum of the indices. We have the sum of this 0 plus 1 is equal to 1. We have 1 plus 0 is equal to 1. Here we have 0 plus 2 is equal to 2, 1 plus 1 equal to 2, 2 plus 0 equal to this 2. Let us see the last expansion, 0 plus 4 we have 4, 3 plus 1 we have 4, 2 plus 2 we have 4 and 1 plus 3 equal to 4, 4 plus 0 equal to 4. So what is happening here? The sum of the indices of each term in the expansion is equal to the index of x plus a. So we have the fourth observation, the sum of indices of x and a in each term of the expansion is equal to the index of x plus a. So this is our fourth observation. That leaves us with the last and the final observation, the coefficients. The coefficient here is 1, coefficients here are 1 and 1, coefficients here are 1, 2, 1. So let us make a note of the coefficients. Okay. So let us take the index and the coefficients. So we have index, coefficients. When the index is 0, observe the coefficient is 1. When the index is 1, the coefficients are 1 and 1. When the index is 2, the coefficients are 1, 2 and 1. So 1, 2, 1. Index is 3. Index is 3. We have coefficients 1, 3, 3, 1. So 1, 3, 3, 1. And index is 4. What is happening? We have 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. Now, observe this set of numbers. Do you observe some pattern here? See, for each expansion we start with 1, we end with 1. Okay? Now what is happening to the terms in between over here? You see, 1 plus 1 gives us 2. Here 1 plus 2 gives us 3. 2 plus 1 gives us 3. Here we have 3 plus 1 gives us 4. 3 plus 3 gives us 6. 3 plus 1 gives us 4. So you see, the terms in between are the sum of the previous two terms of the previous expansion. Yes? So this particular array of numbers is called the Pascal's triangle, or it is also called as the Meru Prastara. Okay? So using this pattern, now I think now it is very easy for us to write what are the coefficients of x plus a to the power 5. So what should happen if I have to write another row, the next row if I have to write? So I will take the index to be 5, index is 5. So what should be my coefficients? I should start with 1, end with 1. So what is happening to the numbers in between? 4 plus 1 gives us 5, this gives us 10, this gives us 10, and this gives us 5. So now let us look at all these observations and try to write the expansion of x plus a to the power 5. Let us see what happens. First let us make a note of all the coefficients. Okay? So we start with 1, our next term has 5, 10, 10, 5, 1. So let us make a note of that. 5, 10, 10, 5, and last term has 1. Now let us go for the first observation here. Index is n, index is 5, so number of terms has to be 5 plus 1, that is 6. So we have 6 terms here. Okay, 6 coefficients are there, so there will be 6 terms. What is happening in the second observation? You see, power of x reduces by 1. So we start with x to the power 5, reduces by 1, so this will be x to the power 4, x to the power 3, x to the power 2, x to the power 1, and the last term will have x to the power 0. Go for the next observation. We have power of a increases by 1. We start from 0. So a to the power 0, a to the power 1, a to the power 2, a to the power 3, a to the power 4, and a to the power 5. Let us see the next observation. Sum of the indices of x and a in each term of the expansion is equal to the index of x plus a. Let us check that. 5 plus 0, 5, 4 plus 1 equals 5, 3 plus 2 equal to 2 plus 3 equal to 1 plus 4 equal to 0 plus 5. All are equal to 5. So now the expansion looks very simple to us. What happens if I increase the value of n to some bigger number? Say if I give you x plus a to the power 20 or x plus a to the power 50, x plus a to the power 90. Then drawing this pattern, writing the expansion becomes again a very lengthy process. And therefore, we make use of the concepts that we have studied in our previous chapters and try to simplify this. Let us make use of the concepts from the chapter combinations and permutations to get these numbers. We know NCR, choosing R objects from N objects, is given by N factorial divided by N minus R factorial into R factorial. And this value R can be anything, any natural, any positive integer from 0 to n. It can be equal to 0, 1, 2, 3 up to the term n. Okay? So now let us make use of this formula and try to get these numbers. We know that NC0 is same as NCN, and that is equal to 1. Observe this properly. Index, this is n. Okay? So this one is nothing but 0, C, 0. You are choosing 0 objects from 0 objects. How many ways you can do it? You can do it only one way. So 0C0 is equal to 1. What is happening here? N is equal to 1. So this is NC. NC0 is equal to 1. Sorry, 1C0 equal to 1, and here 1C1 is also equal to 1. Let's see the next one. N is 2 here. Okay. So this term is 2C0 and this term here is 2C2. What is happening to this term? What is this equal to? If you calculate what is 2C1, the number which comes in between 0 and 2 is 1. So 2C1, if you calculate, it is 2 factorial divided by 2 minus 1 is 1 factorial. R factorial is again 1 factorial. This is 2 into 1, that's equal to 2, and that is nothing but a coefficient here. Okay. So this is nothing but 2C1. For the next expansion, let's see here, N is 3. So we have the first term 3C0, last term 3C3. What about the terms in between? This value is nothing but 3C1, and if you calculate 3C2, you will get it equal to 3. Similarly, for the next expansion, we have the first term 4C0, last term 4C1, but what happens to the terms in between? What are the numbers in between 0? Sorry, this is 4, okay. So what are the numbers in between 0 and 4? It is 1, 2 and 3. So if you calculate 4C1, you will get equal to 4. 4C2, you will get it equal to 6. 4C3, you will get it equal to 4, and the last term 4C4 equal to 1. Let's check the last last expansion that I have written. Okay, we have, this is 5C0, last term is 5C5. What are the numbers in between 0 and 5? The numbers are 1, 2, 3 and 4. So next term, if you observe, this is 5C1. If you calculate 5C2, you will get equal to 10. If you calculate 5C3, you will get 10. 5C4, you will get 5, and the last term 5C5 is equal to 1. So now the expansion looks little simple, and using this we can write the expansions of higher orders. Let us try to write when the index is 7, what should be the coefficients? What should be the coefficients? So the first coefficient will be, this will be 7C0, second coefficient will be 7C1, third will be 7C2, 7C3, 7C4, 7C5, 7C6 and 7C7. So now I give you any number that value of n to be any higher number, you can always refer to this and write the expansion. Using all the observations that we have done earlier, now let us try to write the general form, x plus a to the power n. We'll start by writing the coefficients. Our coefficients must start from NC0 and it has to end with NCn. Okay? And as I said earlier, we are considering n to be positive integers only. So let's take for any positive integer n. Okay? So let's start writing the coefficients. It should be NC0, next term should have NC1, next term should have NC2, and next term NC3 and so on up to NCn. Okay? Now let's write the x terms. Power of x decreases, correct? You start from n, next term will have n minus 1, n minus 2, and the last term it reaches up to 0. So this will have x to the power 0. Okay? Now let's write the terms a. First it starts with 0, increases each time. So we have a power 1, a power 2, etc. It reaches the maximum, that is a to the power n. This general form of the expansion For any positive integers n, x plus a to the power n is equal to nc0 x power n a power 0, nc1 x to the power n minus 1 a to the power 1, etc. ncn x to the power 0 a to the power n. This expansion is called the binomial theorem. Now let us try to solve a few problems. First problem I have, expand x square plus 3 by x to the power 4 using the binomial theorem. I have the expansion over here. N value is equal to 4. In the place of x we have x square, and in the place of a we have 3 by x. Okay. Now let us write the expansion. X square plus 3 by x to the power 4. Now the power is 4. Let's start by writing the coefficients first. So we have 4c0, our first coefficient. Second coefficient is 4c1. Next is 4c2. Next is 4c3. And the last one is 4c4. These are our coefficients. Now our x terms. Okay. In the place of x we have x square. So we have x square. The power should decrease each time. So we start with the highest power, that is 4. In the place of x we have x square. Okay. Now let us reduce the power each time. We have x to the power 4, this will be x to the power 3, x to the power 2, this will be 1, and this will be 0. Okay. Now let us write the a terms. A is 3 by x. So we have 3 by x. I will write 3 by x everywhere first. Okay. Now the power of a increases, yes. So we start from 0. Next term will have the power 1. Here power is 2, 3 and 4. So this is the expansion for x square plus 3 by x to the power 4. Let us now try to simplify this. We need the values of 4c0, 4c1, 4c2, 4c3 and 4c4. Let us try to simplify this. We have 4c0 is equal to 4 factorial divided by 4 minus 0 is 4 factorial into 0 factorial. So this is equal to 1 because 0 factorial is equal to 1. So we have the coefficient here equal to 1. Here for this term we have x to the power 2 to the power 4. It is of the form a to the power m to the power n, and this is nothing but a to the power m into n. Okay, so let us multiply the powers here. This will be x to the power 2 into 4 equal to 8. 3 by x to the power 0, it is equal to 1, so I am not going to write it. Let us calculate 4c1. So we have 4c1 is equal to 4 factorial, 4 minus 1 is 3 factorial into r factorial, that is equal to 1 factorial. This will be equal to 4. So we have 4, this will be equal to x square to the power 3. So 2 into 3 is 6. For this term we have 3 by x to the power 1. So 3 by x will remain, plus 4c2. What happens to 4c2? 4c2 is equal to 4 factorial, 4 minus 2 that is 2 factorial into r factorial, that is equal to 2 factorial. Our answer will be equal to 6. So we have the coefficient here 4c2 is equal to 6. X square to the power 4 is there. So 2 into 2 is 4. So x to the power 4. This will be equal to 3 square by x square, that is 9 divided by x square. Plus let us calculate 4c3. 4c3 will be equal to 4 factorial, 4 minus 3 is 1 factorial into 3 factorial, and the answer will be equal to 4. So we have 4 x square, this will be 3 cube, that is 27 divided by x cube. The last term 4c4 we know equal to 1. x square to the power 0 will be equal to 1. 3 by x to the power 4. So, 3 to the power 4 is 81 divided by x to the power 4. Now, let us multiply the constants here, the numbers here, and cancel out the x terms if we can, and write the final answer. So, this is equal to x to the power 8, this is 4 into 3, that is 12. We can cancel out this term. So, it is of the form a to the power m divided by a to the power n. You can write this as a to the power m minus n. Okay. So, let us use that here. This will be x to the power 6 minus 1, that is 5. So, x to the power 5 plus we have 9 into 6 into 9 is equal to 54. So, we have 54, x to the power 4 minus 2, that will give us x to the power 2. Here we have 4 into 27 is equal to 108. So, plus 108. What will happen here? 2 minus 3 will give us minus 1. So, we know x to the power minus 1 is nothing but 1 by x. So, we can write this as 108 divided by x plus the last term 81 divided by x to the power 4. So, this is our required answer. Next question, let us expand 1 minus 2x to the power 5. Now, n value is 5. So, the coefficients will be 5c0, 5c1, 5c2, 5c3, 5c4 and 5c5. I have made a note of the coefficients. Okay. Now, in the place of x we have 1, in the place of a we have minus 2x. Be careful, take along with the sign. So, a is minus 2x. You have to take x and a along with their signs. Clear? Okay. Now, let us write the expansion. We have 1 minus 2x to the power 5. First, let us write the coefficients. So, 5c0, 5c1, 5c2, 5c3, 5c4 and the last one is 5c5. Now, let us make a note of the x terms. X terms are 1, so we start the power of 1 by 5, the highest power, go on reducing. So, this is 5, 4, 3, 2, 1 and 0. So, for the a term, I will make a note of the a terms first, 2x plus okay. Now, a terms the power goes on increasing. So, we start with the 0, we have 1, 2, 3, 4 and the last one gets the power 5. Okay. So, let us simplify this. 5c0 is 1, 1 to the power 5 is 1. This will be equal to 1 because raised to the power 0. So, the first term is 1. For the second term we have 5c1, we have calculated, we have the 5c1 value is 1, 1 to the power 4 is 1, minus 2x to the power 1, minus raised to the odd power. So, minus term will remain. So, minus into plus will give us minus. So, into 2x plus for this term we have 5c2, 5c2 value is 10. 1 to the power 3 is 1. What happens here? Minus raised to the even power, so it becomes positive. 2 square is 4, x square will remain. Plus 5c3, 5c3 value is 10. Okay. Now 1 square is 1. What happens here? There is minus raised to the odd power, so minus term will remain. A to the power 1 to the power 2 is 1. This will be 2 to the power 3, that is 8, okay, 8 into x cube plus for the next term we have 5c4 value is 5, 1 to the power 1 minus to the power even, so that will be positive. So, 2 to the power 4 is 16, x to the power 4 will remain. Last term we have 5c5 is 1, 1 to the power 0 is 1. This term c minus raised to the odd power, so this becomes minus 2 to the power 5 is 32, we have x to the power 5. Now let us simplify this, let us multiply and write the answers. 5 into 2 is 10, this will be plus 40x square, this will be 80x cube, this one will be 5 into 16 is again 80, x to the power 4 minus 32, x to the power 5. So this is our required expansion.